This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Week 4, Lesson 9. The airside capstone, the pressure budget and balancing. No new formulas. You walk the whole duct system end to end, find the path the fan actually has to fight, size the fan to it, and balance every other branch so all the outlets deliver their design airflow. The idea. Every tool from the week now assembles into one system. The fan has to overcome the critical path, the route from fan to outlet with the highest total pressure loss, not the longest run and not the highest flow run. Size the fan to that path, then balance the other branches up to match it so airflows land at design. The method. Split the critical path into sections of constant velocity and size. In each section, add the straight duct friction to the fittings on that section, all reference to that section's velocity pressure. Sum the sections for the path total. Set the fan total pressure equal to it, then take the air power. Notice the branch here is critical, even though it's shorter than the trunk. Its T and diffuser dominate. The three printed relations. The section total pressure loss is Darcy friction plus the sum of fitting coefficients all times that section's velocity pressure, each coefficient tied to its own section. A single fitting is its coefficient times its velocity pressure. Fan air power is the constant times volume flow times pressure. And for standard air, the general velocity pressure form collapses to the V over 4005 form. Watch the two meanings of V. Velocity in the pressure terms, volume flow in the power. The givens. The critical path is two sections, a rectangular trunk carrying the full flow, then a round branch to the most remote diffuser. Read each section's hydraulic diameter, length, friction factor, and velocity. The fitting coefficients come from the loss coefficient tables. Solve each section. Section A, the friction coefficient is 0.6 plus the elbow times the trunk velocity pressure 0.20 inches. Section B, friction 0.8 plus the T in diffuser times the branch velocity pressure, also 0.20. Each set of coefficients rides its own velocity pressure. Total and fan. The critical path is the sum, 0.40 inches, so the fan total pressure is 0.40. Air power is the constant times the total system flow times that pressure, about a quarter horsepower. Remember, that's air power. Shaft and motor power are larger, and the coil and filter losses from the schedule add on top of this duct budget. Balancing. The near branch reaches its diffuser with less loss, so it would grab more than its share. Its path is only 0.3, so add a balancing damper worth 1/10 of an inch to bring it up to the critical 0.4. Now every path matches, and each outlet delivers its design flow. The traps. Critical means highest pressure loss, not longest or highest flow. Every coefficient multiplies its own section's velocity pressure, not one shared value. A junction splits into a branch coefficient and a through coefficient. Charge each to its own path, never both to one. The 1100 and 4000 constants are not interchangeable. And you size the fan to the critical path. Dampers raise the other paths up to meet it. Recap. Walk the critical path, sum friction plus fittings per section on each section's velocity pressure. Set the fan total pressure to the path total, take the air power at total flow, then balance every other path up. That's the whole airside budget.
The full study guide with every equation and common exam trap is free at peprepengine.com, link in the description. Structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.